Look at the device in your hand right now. Inside of it is a processor with millions of times more memory than the computers that guided humanity to the moon. We take this absolute magic for granted. But that modern miracle, it rests on a terrifyingly fragile foundation. The entire digital age balances on the shoulders of one invisible machine. Without it, the future simply stops. Welcome to today's Explainer, where we're going to uncover the invisible choke point of the global AI revolution.
645 billion euros. As of August 2026, that is the value of a company called ASML, the most valuable technology company in all of Europe. Period. But here's the crazy part. Walk down any busy street, ask 100 people what ASML actually builds, and 99 of them are going to stare right through you. So how does a machine this massive, an engine producing the absolute most vital hardware on planet Earth, remain entirely invisible to the public? Who really controls the planetary scale of today's technology? Well, to figure out this mystery, we have to trace the bloodline of this invisible titan. And to do that, we literally have to go back in time.
Chapter 1. The Leaky Shed.
Okay, let's drastically shift the scale backward. Forget the trillion-dollar global industry of today and step into 1984. Today, ASML operates ultra-high vacuum chambers with atomic precision, pulling in tens of billions in sales. But back then, they were a struggling joint venture operating out of a wooden shed in Eindhoven. And no, that's not a cute corporate metaphor. It was a literal shed. They hung heavy plastic sheets from the ceiling just to catch the rainwater pouring through the roof.
It was a sensory nightmare. The early machines leaked high-pressure hydraulic fluid constantly. Imagine thick oil pooling on the floor, absolutely destroying what was supposed to be a pristine, clean room environment. The hydraulic compressors, they roared so deafeningly loud that engineers literally had to drag the pumps outside and shove them into shipping containers just to hear themselves think. That early machine was a total commercial failure. So think about this for a second. We're looking at a company that couldn't stop leaking oil, couldn't keep the rain off its own tools, and held barely 10% of the market. How in the world did this chaotic, struggling outfit go on to solve the absolute most complex physics problem in human history? Chapter 2. Forging the Impossible Light. This is where our story leaves normal engineering behind and crashes straight into impossible physics. For decades, the industry shrank chips using light to print patterns onto silicon, but eventually they slammed into a hard physical wall, the Rayleigh diffraction limit. Basically, normal light had become a blunt chisel. You can't carve a microscopic 3-nanometer future if your tool is physically wider than the grooves you're trying to cut. The light just bends and blurs. To go smaller, ASML had to abandon normal light entirely. They had to manufacture a kind of light that nature itself never produces on Earth. The magic number they needed was 13.5, specifically 13.5 nanometers. That is extreme ultraviolet light, or EUV. It operates at the absolute bleeding edge of the spectrum, sitting right on the border of soft X-rays. But how do you harness a light that doesn't naturally exist? Well, you have to build an artificial star. Inside a silent, ultra-high vacuum chamber, a droplet of molten tin falls through the darkness. It's microscopic, just 30 microns wide. 50,000 of these droplets fall every single second. Before a droplet can touch anything, an invisible pre-pulse laser strikes it, flattening the tin out. Microseconds later, a massive main laser hits that flattened disk. The impact vaporizes the tin at 220,000 degrees Celsius. That is 40 times hotter than the surface of the sun. For a fraction of a second, humanity manufactures an impossible plasma. And from that microscopic explosion, extreme ultraviolet light is born. But wait, creating the light is only half the battle. Conventional glass would instantly absorb that EUV beam. Even the air we breathe absorbs it. So you have to capture and direct this light using mirrors in a total vacuum. Carl Zeiss built a series of mirrors for ASML that are so utterly flawless, so atomically smooth, that if you blew one up to the exact size of the country of Germany, its largest imperfection would be a single bump just 1 millimeter high. It took decades of research and over 10 billion euros to forge this impossible light. But progress is a brutal, unstoppable engine. So what happens to the mighty technology empires that fail to harness this artificial star? Chapter 3. Graveyard of Tech Giants. We are now stepping into the graveyard of fallen kings. The companies that once ruled the entire world, right up until the impossible light changed everything.
Today, the global high-end lithography market is a picture of absolute untouchable dominance. ASML holds a staggering 90%. The remaining slivers? Those are the shattered remnants of former Japanese manufacturing giants, Nikon and Canon, holding just 5% each. How did Nikon, once the absolute pride of Japanese technology, fall so incredibly far? The industry calls it a textbook-level technological misjudgment. Nikon got trapped by its own past success. They stubbornly clung to their older 157-nanometer dry technology, completely rejecting the new immersion lithography revolution that ASML was championing. By the time the world desperately needed advanced 7-nanometer chips, Nikon's blunt chisels simply couldn't make the cut. They missed the revolution completely. While Nikon was forced into a humiliating retreat back to the older, mature chip markets, Canon took a wildly different survival path. They pivoted to something called nano-imprint lithography. Instead of using light and complex optics, Canon's machines literally stamp the chip patterns into liquid resin at room temperature, almost like a microscopic printing press. It's a fascinating, desperate survival tactic that actually works for less complex memory chips. But try stamping highly complex logic chips, it struggles heavily with crippling defect rates. All right, so Nikon fell. Canon retreated to a niche. If the competitors have all been vanquished, who actually controls the ASML monopoly? The answer is terrifyingly simple. Nobody and everybody. Chapter 4. A Fragile Global Web. Here's the thing. The true suspense of the AI revolution isn't about software at all. It's about physical hardware. And the biggest myth out there is that ASML is this solitary giant that built EUV technology all by itself. Not true. The machine is a physical monument to a deeply fragile multinational supply chain. I mean, just one of these machines is the size of a double-decker bus. It weighs so much that you need 3 Boeing 747 cargo planes and 20 trucks just to move it. Inside that single machine are 457,000 individual components. They come from a staggering 5,100 global suppliers. Lasers from Germany, atomic mirrors from the edge of Europe. Imagine a chain stretching across the entire planet. Thousands of factories, engineers, and laboratories, all perfectly synchronized and depending on each other. Break just one tiny link in that chain, and the machine capable of shaping the future never comes to life. ASML isn't a self-contained manufacturing titan. They are a hyper-specialized system orchestrator. And they knew the astronomical risk of relying on all these other companies, so what did they do? They weaponized that risk. They took massive equity stakes in their own suppliers, like literally pouring 1 billion euros of cash into Carl Zeiss just to fund the optics research. They didn't build a walled fortress, they built a global web, making absolutely sure that the entire semiconductor industry is universally dependent on their collective survival. Today, the stakes are higher than they have ever been in human history. The acceleration is blinding. In April 2024, legendary CEO Peter Wenning handed the reins over to Christophe Fouquet. By 2025, they launched the next generation, high-end EUV, pushing the physical limits of light even further. By August 2026, their valuation hit that jaw-dropping 645 billion euro mark. But they achieved all of this while sitting directly in the crosshairs of a brutal, high-stakes geopolitical chess match between the United States and China. Think about it. Every advanced chip in your phone, every breakthrough in artificial intelligence, every single leap in human computing for the next decade, all of it is balancing on a razor's edge inside a clean room in the Netherlands. We've seen how they conquered the impossible light. But as geopolitical fault lines deepen across the globe, we are left with a chilling question. What happens to the modern world if just one of those 5,100 invisible links shatters?